Hello students, welcome to the class of software engineering. Today let us discuss about structural models. So what do you mean by structural models? Structural models may be static models. So static models means they show the structure of the system design, and dynamic models they show the organization of your system when it is executing. So this is actually your structural model. So two types, it can be static as well as dynamic. Static models, they show the structure of the system design, and dynamic models, they show the organization of the system when it is executing. Now we'll see under the structural models the different diagrams. One is class diagram. So you know what is a class? Collection of objects. So class diagram will mainly show what all classes are used in your system. That is one thing. And also it will show the association between these classes. Association means the type of relationship between these classes. So association is a link between classes that indicates that there is a relationship between classes. There is a relationship between these classes. So we will clearly understand about this class diagram using this figure. Okay. So you can see here patient. This is one class, and another class is patient record. So you have two classes. So they are represented using this rectangular box. Okay. So the figure 7 shows the association between patient and patient record class. So what is this association here? It is 1:1 type of relationship. Can you see here? Here it is written 1. Here also 1. So the association indicates that it is 1:1 type of relationship between objects of these two classes. If I take, that is, you have to clearly understand what is this 1:1. That is very important. So each patient means one patient, na? Each patient has exactly one record. So when I read from this end, each patient has exactly one record. You will agree. And I have to also read from the other end. Each record maintains information about exactly one patient. Each record exactly maintains information about one patient. So from both sides it should be 1:1, no? So you have to check like that. Each patient has exactly one record, and each record maintains the information about one patient. So this is 1:1 type of relationship. So we have different types of relationship. It can be 1:n. You can see here. Other type of associations are 1:n, means one to many, I can tell, or n can be represented as star. That also it can be done. When you indicate star, it indicates indefinite number of objects involved in the association. n:n, many to many, n:1, many to one. So these are the different types of associations. 1:1, 1:n, n:n, n:1. So you have to actually decide what type of association it is. Now how to represent the class diagram? That is very, very important. So just one example we have. Class diagram of banking system. Okay, class diagram of banking system. You can see here rectangular boxes, no? Those represent the classes. So this is one class, bank is one class, branch is one class, loan is another class. These all are classes. So how you are representing it in the rectangular box? So the name of the object class is in the top section. Can you see here? In the top you have the name as bank. That means the name of this class is bank. Now I'll move on to this one. Branch means the name of this class is branch. Similarly, account. The name of this class is account. The class attributes are in the middle section. Can you see the class attributes? Now if I consider this bank class, we can see the attributes are name, code. For this branch, branch code, city. For this loan class, the attributes are loan number, amount, type. For this account class, the attributes are account number, balance. Now, one more thing left out is the operations, or we call it as methods. So methods associated with the object class are in the lower section of the rectangle. Can you see here? Lower section means this one. Add branch, it's a method. Remove branch, it's another method. Get branch, get all branches. Similarly for this branch class, here the methods are add account, remove account, get account, add loan, remove loan, get loan. Okay. So you can see also the relationship or the association is being represented. So in this class diagram of banking system, you can see that you have several different classes. So we have bank class, branch class, loan, account, savings account, current account, customer. And what is in the middle section is the attributes. So suppose if I take this bank class, the attributes are bank name, code, and the methods are add branch, remove branch, get all branches. Okay. And also it shows the association also here between each class. Can you see here? 1 star. Between this bank class and branch class, you can see the association, type of association. 1 is to star. Star is n. Means one bank can have n branches. No? If you consider Canara Bank, it can have n branches. And n branches will belong to one bank. Only one bank. Okay. Then we have one more association. Loan and customer. Loan and customer. So what can you see? Customer can have any number of loans, 0 to star. Na? So star means n. Okay. And then we'll see other types of representation here. We have something called generalization or inheritance. Already you know about inheritance. So another term used for this inheritance is generalization. Same, one and the same, both are. So inheritance is something like you're deriving a new class from already existing class. So that already existing class is called as superclass or parent class. And the new class is called as child class or subclass. Clear? So new class can actually inherit the properties of the parent class. Also it can have some additional features or additional attributes. Now we'll come back to this diagram. Okay, let us come back to this diagram. And you can see here account class. Account class. And just look at this type of notation. This type of notation indicates it is inheritance or generalization. You can see that these two classes, savings account and current account, are inheriting from this account class. So this type of notation indicates generalization or inheritance. So it says that these two, savings account and current account, will inherit from this parent class, that is account. So this is the parent class. These two are the child class. Now this notation is different, okay? These all notations. Now this is mainly inheritance. Okay, so savings account class has two subclasses, savings account and current account. The generalization is shown as an arrowhead pointing up to the parent class. Can you see? It is shown as an arrowhead pointing up to the parent class, pointing to this account class. Next, let us discuss about aggregation. So this is another new terminology in class diagram. Aggregation. So can you see this notation being used in this class diagram? This notation and this notation. So they are different from your generalization notation. Okay. So look at this notation and this one. Both indicate that is aggregation. So what is aggregation? So like one object means one whole object, I can tell. It is composed of other objects or other parts. That is called aggregation. Like for example, if you consider a mobile phone, it is made up of several hardware parts, isn't it? So once we combine it together, we aggregate it together, then we get the one set of mobile phone, isn't it? So it's like composition, I can tell. Aggregation is nothing but composition. So it is composed of several parts. We use a diamond shape next to the class that represents the whole. So we are representing using a diamond shape next to the class that represents the whole. For example, a patient record, this is a class, is a composition of a patient and indefinite number of consultations, I can tell, because summary treatment also you are including in patient record. Na? So patient record is a composition or aggregation of a patient and indefinite number of consultations. Indefinite means here infinite, so it will be star. So you can see the diamond shape is being attached to the whole class, okay, whole, the class which represents as a whole. So same thing, you can also look into this diagram. It is represented here also, diamond shape which will be attached to the class as a whole, branch. So loan. So this branch, it's an aggregation of loan and account, I can tell. So it is composed of loan and account. Okay. Next, we'll discuss about behavioral models. Behavioral models, so which mainly show the organization of your system once it is being executed. So behavioral models are models of the dynamic behavior of the system as it is executing. So they show what happens or what is supposed to happen when a system responds to a stimulus from its environment. So it mainly tells what will happen when your system receives a stimulus. So stimuli are of two types. First one, data. So data is some input, I can tell. Some data arrives that has to be processed by the system. So suppose your system receives some input, then it should be processed and finally you have to get an output. Then events. Some event happens that triggers system processing. So data and input are event are different. Event is some event will occur unknowingly. So some event happens that triggers system processing. Let us discuss about behavioral models. Behavioral models are of two types. One is data-driven modeling. So what do you mean by data-driven modeling? You can understand by the term itself. It is data driven. So data driven models show the sequence of actions involved in processing the input data. So your system will receive some data, which will be the input data. So once it is received, that data needs to be processed. So for that, certain actions might take place. So you have to show the sequence of actions involved in the processing and also finally generating an associated output. You have to generate an output. So for this purpose, activity diagrams are used to represent the data-driven model. So we are using activity diagrams. So activity diagrams mainly show the activities involved in the process. The UML does not support data flow diagram. So earlier we had DFD, data flow diagram concept. So it is one and the same like your activity diagram, data flow diagram. But now in this UML does not support that one. Okay, earlier DFDs were used, but now we are using activity diagrams. Now, reason for this is that your DFDs, that is data flow diagram, focus on system functions, and they do not recognize the system objects. So that is the main reason. Data flow diagram will not recognize the objects, only it will focus on the system functionality. Okay. Because data-driven systems are so common in business, UML 2.0, the version UML 2.0 introduced activity diagrams, okay, which are similar to your data flow diagrams. So we will see one activity diagram. So look at this figure. Figure name is an activity model of the insulin pump operation. So somewhere you have studied about the insulin, that is in the case study of first module. Okay, so here figure 9 shows the chain of processing involved in the insulin pump software. In this diagram, the processing steps represented as activities and the data flowing between these steps is nothing but represented as objects. So here, look at this activity model of the insulin pump operation. So here you have the purchase officer. So filling. So he actually orders, isn't it? Gives the order. So fill in, then it will validate. Then you have budget, data store orders, then supplier. Supplier is going to provide those orders. Now the figure 10 shows the sequence model of the processing of an order and sending it to supplier. So in detail we will see here. You know that actually the sensors will be embedded into the body of the diabetes patient, isn't it? So through this sensor you can calculate the various blood parameters. So you need to get the sensor value, means through that you are going to get the data, sensor data. So you are actually collecting the various blood parameter readings. So in that you can compute the sugar level. So you will get the blood sugar level. Now with respect to that blood sugar level, you have to calculate how much amount of insulin dose needs to be put into the diabetes patient's body. So for that Then we need the insulin requirement. You have calculated how much amount of insulin, no? Then you have to provide that this much dose of insulin is required. That will come under this insulin requirement. So calculate pump commands. So through the pump by sending these pump control commands to the control pump, it will send the insulin dose into the diabetes patient's body. Event driven modeling. This is the next second type of behavioral model. So event driven modeling shows how the system responds to internal and external events. So earlier was data driven modeling. Now what we have is event driven modeling. So here mainly shows how your system will respond to the various internal and external events. Now these events are mainly responsible for the state transition, mainly cause your system to move from one state to another. The standard UML notation for representing event-driven modeling we are using is state diagram. State diagram. So we have earlier in the beginning we have seen there are 5 diagrams which you are going to use in UML. So last one is the state diagrams. So what does state diagram show? The system states, different states of your system and events that cause the transitions from one state to another. So state diagram will mainly consist of the different states of your system, and it will also specify the events that cause the transition from one state to another. So we will see a simple example, that is state diagram of a microwave oven. So now you have the state diagram. This is the state diagram. So look how the event state diagrams are represented. This notation is very important. Okay, whatever notations you are using. So you can see here the filled circle indicates the initial state, and filled circle inside another circle indicates the final state. So you can see the different states in your system. One is waiting state, another one is full power state, set time state, half power state, disabled state, enabled state, operation state, waiting state. So these are the different states, and events are like this: half power, full power, timer. So these events mainly cause your system to move from one state to another state. Let us see the sequence of actions involved in the microwave oven. First thing is, very important thing is, now why this we have taken the example of microwave oven. What is the purpose of microwave oven? The purpose is to cook the food in a given time period, correct? So first, when you all of you have seen the microwave oven. So you have 2 knobs. One is for setting the power, another one is for setting the timer. So first select the power level. That is important. First select the power level. So power level, it can be in this diagram when you see full power, half power. So it's left to you. So first you need to select the power level, that is either half power or full power. Next, second one, input the cooking time using a numeric keypad. Now main purpose is to cook the food in a given time period. So you have to set the time. So either using a numeric keypad, or you might be older ovens might be having a knob. Then after that you have to press start and the food will start cooking for the given time. Okay. So safety. Now here you have to consider safety. That is very important. Safety. For safety reasons, the oven should not operate when the door is open. Do you agree? Yeah. The oven door should be closed when you are operating. So it should not be open. So, and on completion of cooking, a buzzer sound will be given. Okay. So the oven has a very simple alphanumeric display, okay, that is used to display various alerts and warning messages. So display is like alphanumeric, alphabets as well as the numbers. So numbers, you can set the cooking time, and alpha, that is mainly you can display some error message or warning message. Okay, so we'll come back to the state diagram. In this UML state diagram, what can you say is rounded rectangles represent the system states. That is very important. How to represent a system state? Rounded rectangles. You can see rectangles. It looks like a rectangle, but it is rounded rectangle. So rounded rectangles represent the system states. Okay. So they may include a brief description following do of the actions given in that state. So the labeled arrows represent stimuli that force a transition from one state to another. So indicate start and end states using filled circle that we have seen. Okay. Now, let us see in this diagram, this is the initial state, no? So your system is in which state now? Waiting state, okay? So this is state name, waiting. And inside that we have do. Do is something like action. See, they may include a brief description following do of the actions taken in that state. So what it will do? It has to display the time now. Display the time. So here either you can select full power or half power. So this is actually the stimuli or the event. So once this event occurs, some transition will happen. So response initially to either the full power or the half power button. So you can see here, if full power means after receiving this event or stimuli, your system state will be moved to full power, from waiting to full power. So do, what is that? Set the power to 600 watts. Set the power to 600 watts. If you are using half power, if you are selecting, so based on that stimuli or event, your system will move from waiting state to half power state. So here do set the power will be half of that, 300 watts. Okay, can you see here again in these two states the transition occurs? Half power, from full power to half power, again from half power to full power. What does it mean? See, suppose you have selected full power initially and in the middle you want to move to full power, then that is also, half power, then that is also possible. See here, after pressing half power, you'll move to the system state half power, or from half power you want to move to full power means again you press this full power button. Okay. So users can change their mind after selecting one of these and press the other button. Okay. Next, the timer is set. The timer is set. Can you see? Yeah, we are setting the timer. So set time, do get number, exit set time. So you are setting the time, and keep in mind that the door should be closed. If the door is closed, enable, do display, ready. So in the display it will print the message, ready. That means then you can start the process. So it's like that. The time is set, and if the door is closed, the start button is enabled. Pushing this button starts the oven operation. So can you see? So if once the timer has been set and the door is closed, that means you enabled, means start button is enabled. So it will display ready here, ready. And you can start the operation. So in do what you are specifying, operate the oven, operate the oven. So it will start cooking for that specified time. But suppose if the door is open, then you are moving to disabled state. You cannot start the operation. So in the display, we are going to give the message as waiting, like some warning message, waiting. So it's still in waiting state. Now why it's in waiting state? Because the door is open. Okay. So now what you have to do is you have to close the door. Close the door. And then your start button is enabled. Once you have closed the door, the start button is enabled. Again, you can start the operation. Now, door open. When you can open the door, once the entire operation, cooking time is over and a buzzer sound is heard, then you can open the oven's door. So when the oven's door is opened, again it will move to which state? Disabled state. So where you have to wait. Okay. Now, this is the end of the cooking cycle and the system returns to the waiting state. Clear? Any doubt? No. Okay. Now we'll see the tabular description, okay, of each state and how the stimuli that force state transitions are generated. Okay, now first I'll discuss about the states. Next we'll move on to the stimulus. Okay, first state, waiting state. That was the initial state. The oven is waiting for input. The display shows the current time. So you can see here, do display time. So what is the current time it will display? Now it is 1:30, 10 minutes I want to cook the food. So by 1:40 it should be completed. Half power, next state. The oven power is set to 300 watts. The display shows half power. Okay, full power. The oven power is set to how much? 600 watts and the display shows full power. Okay. Now set time. The cooking time is set to the user's input values. So this time is being set by the user. So either 10 minutes or 20 minutes he has to specify. The display shows the cooking time selected and is updated as the time is set. Timer is set. Next state is disabled. Oven operation is disabled for safety. So oven's operation is disabled for safety. Why? See, if the oven's door is open and you want to cook the food, then it's not possible. So for safety purpose, see, interior oven light is on. Display shows not ready. It is not ready. So you cannot press the start button there. Enabled. Oven operation is enabled. Interior oven light is off. Display shows ready to cook. Then you can press the start button. Operation. One more state you can see, that is operation. So oven is in operation now. Interior oven light is on. Now the oven light is on. Display shows the timer counted on. On completion of cooking, the buzzer is sounded for 5 seconds. So oven light is on. Display shows cooking complete. while buzzer is sounding. So here the oven is in operation when the oven's door is closed. You press the button, so oven will move to which state? Operation state. So it will start cooking the food. So the interior oven light is on there. So the display will show the timer counted down. Okay, display will show like 10 minutes, then it will show 5 minutes left. It start decreasing here. On completion of cooking, the buzzer is sounded for 5 seconds. So buzzer will sound for 5 seconds, which indicates that the cooking process is completed. Oven light is on. Display shows cooking completed. And after the buzzer sound finishes, then only you can open the oven door. Okay. Next. These are the different states. Now next, left out is the stimulus. So we have seen the different states in the microwave oven. Now next we'll see about the stimulus. So different stimuli. So first one is half power. So can you see here in the diagram, once the stimuli half power is received, your microwave oven state will move from waiting to half power. Means half power button has been selected. The user has pressed the half power button. Same thing now, full power. So here it is the full power, no? So after receiving this stimuli full power, the microwave oven state has been moved to full power state. So here the power is set to 600 watts. If it is half power, the power is set to 300 watts. Next timer. Next stimuli is timer. Okay. After receiving this timer, so it will move to this set time state. Yeah. So what is this timer? User has pressed one of the timer buttons to set the time. So we have one more stimuli. Can you see here? Number. Okay. So that stimuli, the user has pressed a numeric key for actually selecting how much time, isn't it? Next, which are other stimuli? Yeah, door open, door closed, start. Okay, we'll see that one. Door open means the oven door switch is not closed. And door closed means the oven door switch is closed. Start means the user has pressed the start button, so it can start the operation. Cancel. Can you see one more button? Cancel. What is that? It will cancel. Yeah. So user has pressed the cancel button. So these are the different states and stimuli for the microwave oven. Okay. So this is mainly the tabular description of each state. Thank you.